So analytics is all about variables. So we will be analyzing in terms of the variables. So if we look at the variables, we can classify them as qualitative variables or quantitative variables, and also as dependent variables and independent variables. When you come to qualitative variables, we can further classify them as nominal or ordinal. Ordinal means you can order them, nominal means you cannot order them. Suppose say marital status, married and unmarried, or gender, male or female. Can you order them? No, it's not like one comes higher and the other comes lower. It's not that way. So we cannot order them. But still, they are qualitative variables and they are nominal variables. Whereas ordinal variables can be ordered high, medium, low. You can put high at the top, medium in the middle, and low at the bottom. Uh, and another example is uh, good, better, best, something like that. Uh, so these are ordinal variables which can be ordered or you can rank them, whereas the nominal variables are similar but they you cannot rank them. Uh, quantitative variables deals with numbers or data. I mean, and further they can be classified as interval variables or ratio variables. So what is dependent and independent variable? Here we have got an example. Crop production. The crop production is a dependent variable. On what is it dependent on? It is dependent on rainfall. It is dependent on fertilizer usage. So rainfall and fertilizer usage are independent variable, and dependent variable is crop production. So we'll see more examples of these: dependent, independent, qualitative, quantitative. Okay, got some idea? So let's move on. So here we have got some examples of our dependent and independent variables. The treatment for cancer, how the drug has an impact on a cancer patient. Here, the independent variables are dosage and the timing. The dependent variable is the impact the drug has on cancer. You can call it response of the patient to the treatment or something like that. So that is dependent. Another example is, okay, the third example is how many days people can eat soup until they get sick. The independent variable is the number of days of consuming soup. The dependent variable is the onset of illness. Just some little examples I've just put here. Now, going further, the qualitative variables that we saw here, the qualitative variables, this is the first box. We are further dealing with it in greater detail. Qualitative variable, as we said, nominal, ordinal, there could be something called dichotomous as well. So a nominal variable has two or more categories, but there is no intrinsic ordering. That's what I mentioned. There is no ordering to the categories. For example, the categories male and female, there is no ordering there. For example, if you take hair color, blonde, brown, brunette, red, these are all hair colors. But can you order them? Can you rank them? Which is good or which is bad or which is high or which is low? You cannot rank them. So that is another nominal variable. What is dichotomous variable? Ordinal we have seen. What is dichotomous? Dichotomous variables are also categorical variables. Categorical in the sense qualitative variable. Okay, when I say qualitative, it is also called as categorical variables. Dichotomous is a categorical variable which has two categories, only two categories: yes, no, up, down, on, off, things like that are dichotomous. Okay, here we have got a example. If we have asked a person whether they owned a mobile phone, what do you expect as the answer from that person? It could be either an yes or a no. So it is two. Only two levels are possible in a dichotomous variable. Such variables are called dichotomous. And if you ask where the movement of the lift, whether it goes up or down, probably up or down is the only thing. Probably, I'm just giving you some example. Probably it's stationary on a particular floor or also there, but that we are not interested in capturing. The categorical variables can have only two levels: yes, no, on, off, up, down, something like that. These are categorical dichotomous variables. Ordinal variable, as we have seen, you can order them. One example is low, medium, high. Three categories. Here we have three categories. It could have any number of categories, but you will be able to rank them or order them. So that is ordinal variable. Okay. Now these are interval variable is a quantitative variable. Here we measure in terms of numbers, in terms of quantitative values. We can quantify them. If you ask a person what is your salary, he may say 10,000, 15,000, or 20,000, whatever it is. So that is a quantity. You are able to quantify it. So that is why it is a quantitative variable. Here we also have in something a special case called interval variables, where if you are expecting a quantitative variable to be in multiples of say 5,000, then you can term it as an interval variable. It's a special case of quantitative variable. If you are expecting the salaries of people or persons in your employees in your organization to be in multiples of 5,000, such as for example, one employee gets 10,000, the other gets 15,000, the other one gets 20,000, in intervals of 5,000. There is an interval between these things. So such case of special variables are called interval variables. Ratio variables, it has all properties of an interval variable. Maybe it can also be termed as an interval variable, but what makes it a ratio is uh, uh, as a clear definition of zero. When the variable equals zero, there is none of that variable. Suppose height. If you say height is zero, does it mean anything? No, that variable is becomes redundant or meaningless. But you can say salary as zero. Probably you don't get a salary, but that's not a ratio variable. But here in this case, a ratio variable. When you say weight of a person is zero, does that exist then? It doesn't exist. So that is the difference between ratio variable and interval variable. So these are just concepts, probably more a theoretical concept. Uh, but just keep those concepts at the back of your mind. But is what you can do. Now, what we have seen is nominal and ordinal belonging to qualitative variable, interval and ratio belonging to quantitative variable. On a quantitative variable, these are numbers, these have a range, these have a mean. So you understand probably when we say there is a median, that you could calculate percentiles on them, you could add or subtract them, you can have a median or standard deviation, you can have a coefficient of variation. All these things are applicable for ratio variables, but interval variables you can't have a ratio. Where is it? Interval variables. These are interval variables. You cannot have a ratio. You cannot probably. So that's the definition of it. You don't have to get too. Uh, no. So this is a simple tabular column which says what you can compute for each of these variables. If it is a nominal variable where you cannot order them, such as the color of the hair or something like that. You can only do a frequency distribution. Suppose say there in a population there are 10 people, or in a sample there are 10 people with different colors. You can say black color hair is 3, gray color hair is 2, brunette is 1, and something like that. Frequency distribution you can do. But ordinal you can definitely do, and other variables also you can do. Median, percentiles, all these things you cannot do on a nominal. On an ordinal you can do a median and percentile, in the sense median which occurs in the middle, which occurrence comes in the middle, something like that, because you are already ordering it. Ordinal means you are able to order it, rank it, so you'll be able to get a median out of it. And addition, subtraction, of course you can't do. So this is a tabular gist of what you can do and what you cannot do with the qualitative and quantitative variables. Getting into our first topic, measures of central tendency. When I say mean, do you think it is something centric to data? When I say mean, it is an average. It is a when I say average, it is a measure of the central tendency. By central tendency, what you mean? It is taking the mean of all the observations. That means how central the average is central to the observations. Okay, hope you can understand. So the median is also similar. Mode is also similar. So what are the three measures of central tendency? Mean, median, and mode. So mean, median is the one that occurs when you have sorted the numbers in an ascending order. The one that occurs in the middle of the set of numbers is the median. And how do you calculate it? N plus 1 by 2. That is the formula. Mode is the number which occurs most often in the collection. Suppose here, in this example, 6 occurs 4 times, and that's why the mode is 6. Those 7 occurs 2 times, 12 occurs 2 times, they are not the mode. But 6, which occurs 4 times, that is the mode. So it is a measure of central tendency. Going to the next thing, it's the measure of spread. Range is a measure of spread. What is a range? It is the smallest interval which contains all the data. Yesterday I was mentioning an example where the score of students in 100 students in an exam is the lowest is 40 and the highest is 60. So the interval is 40 to 60, and the value of the range is 40 to 100, sorry. The value of the range is 60. So this is the interval in which you can map the marks of all the students. So that means the range is 100 minus 40, that is 100 minus 40, that's 60. Similarly, here we have got an example. The temperatures are here listed down. The highest is 35, the lowest is 20, so the range is 15. 35 minus 20 is 15. So what it means, all the values occur over a spread of 15 degrees. Similarly, all the marks occur over a spread of 60 marks, a score of 60. So that is the range. Now quartiles, I think we have seen it very elaborately while discussing the box plots. Uh, the quartiles, the 3 points. The first quartile, second quartile, third quartile. First quartile, there is for the second quartile is the median, and the third quartile there is at the 75%, first quartile at the 25%, median or the second quartile at the 50%. Interquartile range is Q3 minus Q1. That is the third quartile minus the first quartile. Okay. And measures of spread, again, you have something called percentiles. I think we have covered this as well yesterday very elaborately. Uh, This one, a student, if he says he has got 95 percentile in an exam, it means 95% of the students who appeared for the exam obtained marks lower than that person. So that's what 95% means. 95 percentile, not percentage. So, but the percentage even could be 40 or 45 out of 100, but still he could have been ranked as 95 percentile. Even that is possible. So that's a difference between percentage and percentile. Now here is an example of another measure of spread, absolute deviation, mean absolute deviation. Uh, how do you calculate the absolute deviation or mean absolute deviation? Both are measures of spread. And how do you calculate? This is the number listed here. The mean of this, we know how to calculate. Just sum it up and divide it by the number of entities there, and you get 56. And if you take the value and do a value minus mean, you get these numbers. I've just illustrated in a sort of an Excel sort of a scenario so that you can easily understand. The absolute is just remove the truncate the minus sign. uh, Mean absolute deviation is, I think you just take the mean of it. Mean absolute deviation, you just take the mean of it. So that is how you get 3.75. We can see as an example as well in R, how do we do all these functions. Let's cover the other measures of spread as well, just in case if anything else is there. Variance and standard deviation are also statistical measures of dispersion, or measures of dispersion in the sense measures of spread. How far from the mean uh, a particular sample is located. So that is a measure of a spread. So how do you calculate how many standard deviations from the mean this sample, the value of the sample is? So that you can calculate in terms of number of standard deviations from the mean. So here we have got a derivation about how you calculate variance and standard deviation and mean absolute deviation. All these things we have got here. So how do you calculate for those who need a brush up of the high school math? How you calculate variance and standard deviation? Yes, small illustration here. This is again the same numbers: 52, 52, 48, 60. All these numbers all the way to 62. And if you, I know you can take a mean. It's 56. Well, this 56 minus each of these numbers, you get value minus mean. These numbers you get. Absolute deviation is just truncate the minus sign. Square of absolute deviation. Now you get into a sort of variance. You are getting into computing the variance. When you try to compute the variance, you start taking a square, 16, 8, 64, all these squares. Uh, and variance is sum of square of AD. Just sum it up all together divided by number of entities, and that you get as the variance. Okay, I am not trying. I'm not going to give you a definition of variance, but I'm going to. I'm what I'm trying here to illustrate how variance is computed, so that this can be easily this concept can be retained easily as compared to a definition of a variance. Similarly, standard deviation is just remember it's square root of variance. Okay, so you get this. And mean absolute deviation, this is the same as what we did in the last slide here. This is the same one. So this is how we calculate the variance, standard deviation, mean absolute deviation, and all those things. These are all measures of spread, and we'll be dealing with all these things uh, most often in our statistics and analytics. Okay, before we get into R, let's also see there are something called measures of symmetry. Okay, to better illustrate this, I think I'll move on to the next slide, or probably this slide. Okay, so what is this curve, bell curve? It's a normal distribution curve. Okay, what is a normal distribution curve? We are definitely going to get into this normal distribution at a later point, but once again, probably even now, I will just let you know what a normal distribution is. In real life, practically in the real world, you find by nature many observations are normally distributed, or they tend to be normally distributed. Okay, for example, if you take the population of India, and if you measure the height of each and every one in the population, in the entire population, you would arrive at a mean. Okay, based on the height, you divide by the number of pop, you will have a mean height of a uh, citizen of India, and you capture it here. That will be the mean here at the center. Here, see my cursor, the mean will be here. And when you plot the heights of the other citizens on the same graph, they tend to be closer to the mean. That means those who are uh, too tall as compared to the mean height of an Indian citizen are less in number. They fan out here. You see, they fan out. And similarly, those who are too short as compared to the mean height of the Indian citizen in India will be again fanning out to the left side. That means they here the probability of finding persons who are too short or less, but more often the entire population tries to converge towards the mean. If you plot their heights, they tend to be plotted towards the mean, because here this is the mean, this vertical line. They tend to be more closer to this. You find a lot of people in this area as compared to this area, the fanned out areas. Okay, this is a very naturally occurring phenomena. uh, or even if you consider it to be a phenomena outside of statistics, it's still good, in the sense like it still holds good. But from a statistical point of view, this is a key phenomenon based on which most of our statistical analysis will take place. A normal distribution curve, a bell curve, or a Gaussian curve. This is called a guy called Gaussian. He invented or discovered this phenomena. So it is named after him as a Gaussian curve. So this is a very key uh, phenomena to be understood, not only in analytics or not only in statistics. This is a natural phenomena occurring in our world. You can take, I just took an example of height of people of India, but you can take many other examples as well. But only condition is that if you want to get a proper normal distribution, you need to go with a bigger sample. You can't pick just 10 guys in India, measure the height, and try to plot them and come back and say they don't fall on a normal distribution curve. You can't do that. The sample should be huge, or the population, or it could, if you can manage to do for the population, it's good. But normally what happens is we sample them, because always Doing the entire exercise for entire population is probably impossible. So we try to do samples. So this, if the sample size is huge, then you still arrive at something called as a normal distribution or a bell curve. Okay. So now that you know what normal distribution is, uh, if it is a perfectly normally distributed, uh, if it is a perfect normal distribution or a symmetric distribution, the mean, median, and mode stay here all at one place. Whatever is the mean, that will be the median. Whatever is the median, that will be the mode. Okay, it is called a symmetric distribution. Okay, that is one example. But you may also find a bell curve based on your sample that you got. It is something skewed. This is negatively skewed. Negatively skewed means what happens? The mean will be less than the median. Mean will be less than the median value. Or we can say it the other way as well. Uh, Negative skewness indicates that the mean of the data values is less than the median, or probably median is greater than the mean, but all take the mean as a reference. And as you see in this diagram, the mean is less than the median value because it is negatively skewed, because it tends to give fan out more towards the left. That means it's negatively skewed. And if it is positively skewed, it gets fanned out towards the right. This is the example of a positive skewness here, positively skewed. Okay, this is a measure of symmetry. So what we are seeing is the measures of symmetry, and we are seeing positive skewness and negative skewness and what it means. If it is positive skewness, it means the mean is greater than the median. Okay, the median is, if you consider the median to be here, the mean will be on the other side here, the positive skewness. You can it's out of a little bit of imagination, you will be able to appreciate this concept, why mean median varies when there is a positive or negative skewness. Okay, this is about measure of symmetry, skewness. And the same curve, this is a normal distribution curve, like if we assume, based on the peakedness. If it is too peaked, then you have uh, uh, you measure it with something called as kurtosis. Okay, the kurtosis is a measure of peakedness of the data population. If it is too peaked, then you say leptocrutic or positive peak, positive kurtosis. If it is like a plateau, as you see this blue line, like a plateau, no less than the standard normal distribution. Standard normal distribution is the green one. Okay, if it is less than that, then you say platycritic, because it looks like a plateau here. And it is it, you can also say that it is negative kurtosis. Okay, if you measure a kurtosis, if its value is plus anything with a plus sign, then you say it's a positive kurtosis. That means it is leptokurtic. If you have a kurtosis with negative sign, it means platykurtic, or you can also say negative kurtosis. So this is an example here. 1.25, this is plus. You can see it's leptokurtic. Uh, you really don't know how peaked it is, but by the measure of the kurtosis, you can say whether it is platykurtic, leptokurtic, or mesokurtic. So what is it if it is going to be a perfect distribution without any peakedness? What will be the kurtosis value? This is a question to you. If it is positive, it is leptokurtic. If it is negative, it is platykurtic. If it is a perfect normal distribution or mesokurtic, what will be the kurtosis value? It should neither be positive nor negative. What is the exactly? Vignesh, you are right. It should be 0. If it is 0, then it is mesokurtic. Okay. Mm, so before we get on to the next thing, let's quickly see some concepts. We'll try to do it in R. So this is an example of a dependent and independent variable. Here x is c1 to 10, y is x square. So what is dependent variable here and what is independent variable? There are two variables, x and y, which is dependent and which is independent. Here, because y is dependent on x, there is an inbuilt formula here. That means it is dependent. So this is a mathematical example of what a dependent and independent variable is. And all the learning, theoretical learning that we did so far in terms of trying to understand dependent and independent variable, uh, we'll be eventually capturing it in terms of equations or statistical formulas like this. So we need to extrapolate our theoretical understanding to what we need to capture, how we need to capture it here. Okay. Measure of central tendency. What I'm assigning, this is a vector x, 1 to 10 I'm assigning, and I'm going to, I don't need this. I'm going to assign 1 to 10. Mean I'm calculating 5.5. How did it do? Sum of all the numbers divided by the number of numbers, that is 10. I think all numbers put together should be 55. The total number of 10, and that's how it's getting 5.5. Median 5.5. Mode, you just need to remember that to fetch mode, what we have got here is we are trying to create a function to derive mode. Okay, this is the function that we have written. What it does is, you can, as you can see here, UA, unique UA, some simple function tablet 1 2 3 4 5 6. This one gives 1 1 2 1 2 3 1 1. What does this mean? Tabulate means one occurs how many times, two occurs how many times, three occurs how many times, four occurs one time, five occurs one time, six occurs one time. That's what tablet does. Okay, and which is the maximum out of this three, and when I subset the UA with this, then it gives me the mode. Okay, so it is a simple derivation that we have done. So once you have created a function, you pass the vector. A is the vector. I pass it to the function mode, and it finds the mode for me. Okay. So, and the measures of spread. Range. You know what a range is. So this is how it works: 20 and 35. Our smallest is 20, and the largest number is 35. That's how it's quantile or quartile. This is a data set, and I'm trying to find a quantile or a quartile based on that. Here 0%, 25%, 50%, 75. The first quartile is 25%. Here 2.16275. The second quartile is 50%. The third quartile is 75%, 4.45245. So this is how the quantiles are can be obtained, and mean absolute deviation. There is a function called MAD, mean absolute deviation, or by default it captures median absolute deviation. Okay, median and mean. How does it work? MAD, we have seen that, right? Illustration in the Excel sheet. So that is how the same example we have got it here. Okay. So this is median absolute deviation, that is 4.4478, and this is mean absolute deviation. You need to give center is equal to mean for it to compute mean absolute deviation. And similarly, we can do this with formulas as well. You can write a separate formulas for that. And now with empty cars dataset, I am attaching empty cars so that I don't have to explicitly say empty cars dollar MPG. I just say MPG and I'll be able to do go ahead. So max MPG, of course, I don't have to display the empty cars dataset. Probably by now you know what MPG and other things are. So max MPG, what is the best mileage? It's 33.9, minimum mileage 10.4, mean mileage 20.09, median 19.2, variance 36.321, square root of variance, that is your standard deviation 6.02, sum MPG for just I just summed it there. It doesn't give any it doesn't have any statistical significance why you need to sum an MPG, but still for standard deviation 6.02, that's what we have got earlier. Square root of variance, same thing. Mean absolute deviation, uh, and this is the quartiles. The 10.4 is the lowest, 33 is the highest, first quartile, second quartile, third quartile. Okay, and I finally detach empty cars. And what we have done is separately executed each of these functions, max, min, mean, everything. But in case you want to just get it in one shot by executing a single command, you just need to say describe empty cars and it pulls everything for you here. MPG, you got a mean, standard deviation, median, mean absolute deviation, minimum, maximum, range, skew. Kurtosis also you got. Uh, what else? And something called SC. Okay, so all these things are in one shot. If you want to extract, then you use the describe function. You can get this. So all are positive. So just for analysis, skewness, all are positive skewness except one which is negatively skewed, cylinder that is negatively skewed. So you should be able to imagine how a positive skewness will work or will look like, and a negative skewness will look like. A negative skewness, the distribution will fan out towards the left. Positive skewness, the distribution will fan out towards the right, more towards the right. And similarly, kurtosis, all are negative kurtosis except for one, which is positive kurtosis. That means it is this is leptokurtic. All the others are platykurtic. And yeah, this one is a good example of a leptokurtic or positive kurtosis. Okay, all these details you can get by just executing one command, that is the describe on the empty cars or any data set that you want to analyze. Okay, this is a quick analysis you can do based on this.
I'm sure you enjoyed learning from this video. Please like the video, and if you have any doubts regarding this video, please comment us in the comment section, and don't forget to subscribe to our channel for more such informative videos. Do look out for other related videos in our playlist. For more information, visit our website now. Keep learning with Intellipaat.